Chapter 1 Reaction Kinetics 1.1 Reaction Rate 1.2 Collision Theory 1.3 Factors Affecting Reaction Rate. Reaction kinetics is the study of reaction rate, or how fast a reaction goes. There are a lot of reasons why one chemical reaction might happen. So today let's learn about subtopic 1.1. Reaction rate. Reaction rates are generally measured as changes in concentration of reactants or products as a function of time. Consider a reaction of A produced B. When reaction occurs, concentration of reactant A is decreased with time, while concentration of product B increased with time. The unit of reaction rate. Refer to the reaction A produced B. The reaction rate measured as change in the concentration of each reactants or products over the change in time. For reactant A, rate equal to change in concentration of A over change in time. Negative sign indicates concentration of A decreased with time. For products B, rate equal to change in concentration of B over change in time. Positive sign indicates concentration of B increased with time. The unit of concentration is molarity. The symbol is capital M. The unit of time is second, minutes, hour, day or year. So the unit of reaction rate is molarity per second, molarity per minutes, or etc. Differential rate equation shows the relationship between the rate of disappearance of reactants and formation of products. Refer to the reaction. 2 moles of A produced 1 moles of B. So we can write rate of disappearance of A. Rate equal to negative 1 over 2 dA over dt. Negative sign to show disappearance of reactant. Rate of formation of B. Rate equal to positive dB over dt. Positive sign to show the formation of B. For example, reaction between 2 moles of hydrogen sulfide and 3 moles of oxygen to form 2 moles of sulfur dioxide and 2 moles water. So we can write the differential rate equation as rate equal to negative 1 over 2 dH2S over dt equal to negative 1 over 3 dO2 over dt equal to positive 1 over 2 dSO2 over dt equal to positive 1 over 2 dH2O over dt. If we know the reaction rates one of the substance, we can calculate the reaction rate for other substances. Rate law is an equation that relates the rate of a reaction to the rate constant and the concentrations of the reactants raised to some powers. Let's say we have the following general reaction: A plus B produced C and D. We can write the rate law as rate equal to K time concentration of A to the power of M time concentration of B to the power of N. K is rate constant, which is proportionality constant between rate and concentration for a given reaction and temperature. It does not change as reaction proceeds. M is order of reactions with respect to A. N is order of reactions with respect to B. Reaction order are not related to the stoichiometric coefficient from chemical equation and must be determined experimentally. M plus N is overall order of reaction. Let's look for the example. 2 moles of nitrogen monoxide react with 2 moles of hydrogen and produced 1 moles of nitrogen and 2 moles of water. Given rate equal to K time concentration of nitrogen monoxide to the power of 2 and time concentration of hydrogen to the power of 1. The reaction is second order with respect to nitrogen monoxide, first order with respect to hydrogen. An overall reaction is third order reaction. Reaction order shows how the rate affected by reactant concentration. When double a concentration of reactant, what happens to the rate? If the change doesn't affect the rate, it is zero order. If the rate double, it is first order. And if the rate quadruples, it is second order. From the graph rate against concentration, we can see how the change in concentration affect the rate of reaction. Now let's discuss how to determine the order of reaction with respect to each given reactant by using initial rate method. From the experiment's data we can use concentration measurement to find initial rate. Use initial rate from several experiments to find reaction order. Use the values from any experiments to calculate rate constant, K. Let's look at some sample data of initial rate from the reaction between fluorine and chlorine oxide and try to find the reaction order for each reactant and rate constant. From the equation we can write the rate law as rate equal to K time concentration of fluorine to the power of X time concentration of chlorine oxide to the power of Y. To find the order in fluorine, we use the experimental data with concentration of chlorine dioxide constant. We can see the data from experiment 1 and experiment 3, which is concentration of fluorine double and concentration chlorine dioxide constant. To solve the values of X, rate 3 divide rate 1. Insert the values of concentration for each reactant and rate from the experimental data given. From the calculation X equal to 1 that mean first order with respect to fluorine. To find the order in chlorine dioxide we use the experimental data with concentration of fluorine constant. We can see the data from experiment 1 and experiment 2, which is concentration of chlorine dioxide change and concentration fluorine constant. To solve the values of Y, rate 2 divide rate 1. Insert the values of concentration for each reactant and rate from the experimental data given. From the calculation Y equal to 1 that mean first order with respect to chlorine dioxide. Since the value of X equal to 1 and the value of Y equal to 1, the rate law we can write as rate equal to K time concentration of fluorine time concentration of chlorine dioxide. From the data of initial rate we can calculate the values of rate constant. Just plug in the rate and concentration from any one of the experiment and solve for rate constant K. For the example we use the data from experiment 1. The rate constant equal to 1.2 over molarity times second. While discussing the rate constant we should understand that units for rate constant will be specific to the overall reaction order. For zero order they will be molarity per second since a zero order doesn't depend on concentration. For the first order it is per second, and for the second order it is 1 over molarity times second. For a given rate law, rate equal to K concentration of A to the power of 3. What is the unit of K for third order reaction? Substituted the unit of rate and concentration into rate law. So you can solve the unit of K. For third order reaction, the unit of rate constant is 1 over molarity squared times second. If we want to discern the concentration at any given time, we can use integrated rate law. Integrated rate law show the relationship between the concentration of a reactants and time. We will use different integrated rate laws depending on the overall reaction order. For zero order, concentration A naught minus concentration AT equal to KT. A naught is initial concentration while AT is remaining concentration at certain time. For first order, ln concentration A naught over concentration AT equal to KT. For second order, 1 over concentration A T minus 1 over concentration A note equal to KT. The great thing about these integrated rate laws is that they can be plotted in y equal to mx plus c format to give us a linear plot. For zero-order reaction, concentration versus time gives straight line with negative slope. For first-order reaction, ln concentration versus time gives straight line with negative slope. For second-order reaction, the 1 over concentration versus time give a straight line with positive slope. When we have the data change in concentration and time, we can try to plot according to this different relationship, and the one that gives a straight line will tell us the overall reaction order. This is graphical analysis to determine reaction order from integrated rate law. From integrated rate law we can calculate the half-life. Half-life, or T-half, is the time required for the concentration of a reactant to decrease to half of its initial concentration. Different integrated rate law resulting the different half-life. For zero-order reaction, T-half equal to initial concentration over 2K. For first-order reaction, T-half equal to ln 2 over K. For second-order reaction, T-half equal to 1 over K time initial concentration. We also can determine the order of reaction using half-life graphical analysis. Plot the graph concentration again time. If concentration again time give a straight line with negative slope, it is zero-order reaction. Refer to time taken for first half-life and second half-life. If first half-life equal to 2 times second half-life, it is zero-order reaction. From the graph concentration again time, determine to time taken for first half-life and second half-life. If first half-life equal to second half-life, it is first-order reaction. From the graph concentration again time, determine to time taken for first half-life and second half-life. If second half-life equal to 2 times first half-life, it is second-order reaction. Thank you for listening and watching. Don't forget to answer the formative assessment.